Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Lecture 3, differentiation rules. So today we're going to go over the basic differentiation rules, the most common ones that you'll use on a regular basis. And I'll prove the rules to be true, or at least I'll attempt to. Let's start with kind of the easiest rule, which is, what do they call it? Constant derivative rule? I'm not sure. Something to the effect of, if f of x is equal to a constant, let's say c, then f prime of x is equal to 0. I guess I should probably remind everyone first of what our definition of a limit is, or a derivative, right? Derivative, of course, is the slope of the tangent line, as we learned last time, and we define it like this. The definition of the derivative, f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x, all divided by delta x. And of course you can see that the problem here is that the delta x is going to 0, and you really can't divide by 0, right? Especially if the numerator is going to go to 0. Let's use this formula though to prove this first statement, that if f of x is equal to a constant, then the derivative of a constant basically is 0. So proof. We need to show what the limit as delta x approaches 0 of, well, f of x plus delta x. Well, f of x is just c, and so if I replace x with x plus delta x, I still get c, right? Minus f of x, which is c, divided by delta x. But this is identically 0, right? This is just equal to the limit of 0 divided by delta x as delta x goes to 0. Now, that's different than, say, if we had delta x in the numerator, right, which goes to 0 as delta x goes to 0. This is identically 0, and so this is equal to 0. That one's pretty straightforward. The next derivative rule that's important is, what is the next one? Probably power rule? I think power rule. If f of x is equal to x to the n, then f prime of x is equal to n times x to the n minus 1. So this is called the power rule. This will kind of be your bread and butter rule. Okay, you'll use this quite a bit when working with polynomials. But can we show that it's true? Well, again, we'll go to the limit, right? So f prime of x is going to be equal to the limit as delta x approaches 0 of f of x plus delta x. So that's going to give us x plus delta x to the n minus f of x, so minus x to the n divided by delta x. And so here we're going to have to employ the binomial theorem. The limit as delta x approaches 0 of, we'll have x to the n will be the first term in the binomial expansion of x plus delta x. Remember, delta x is going to be getting very small, so the binomial expansion is justified. The next term will be n choose 1 times x to the n minus 1 times delta x to the 1. The next term will be n choose 2 times x to the n minus 2 times delta x squared. And I'm just going to write plus dot dot dot. We've got many more expansion terms in there. And then finally we've got the minus x to the n. And all of this, of course, is divided by delta x. So you can see that the x to the n term on the end and the x to the n term at the beginning are going to cancel out additively, right? Yeah. And we'll be left with this middle stuff here, right? So we'll be left with the limit as delta x approaches 0 of n choose 1 x to the n minus 1 delta x plus, I'm going to just write delta x squared times a bunch of stuff. It's all these extra expansion terms. N choose 2 x to the n minus 2 times delta x squared plus n choose 3 x to the n minus 3 times delta x cubed, all the way to infinity, right, and beyond. So lots of terms in there, and of course all of this is divided by delta x, right? Well, we can see what that's going to do here, right? We can divide this through term by term. It'll get rid of the delta x here, and it'll reduce this delta x to just delta x times a bunch of other stuff that's got delta x in it inside the parentheses, right? But in the limit, right, as x approaches 0, this term has no delta x in it. So this is fixed. This term here, right, will go to 0. And so all we're left with in the end is n choose 1 of x to the n minus 1. And what is n choose 1? You might recall that the definition of that, n choose k, is n factorial over, in this case, well, it's just right. It's going to be n choose 1 will equal n factorial divided by 1 factorial times n minus 1 factorial, right? So I can rewrite this as n times n minus 1 factorial. These cancel. 1 factorial is just 1, and so you see this is just equal to n times x to the n minus 1. And there you have it. That's the power rule. All right, that was the power rule. All right, the third differentiation rule that I want is to f of x equals c times g of x, then f prime of x is equal to c times g prime of x. So to prove that, it's pretty straightforward. Applying our theorem again, that the derivative is equal to the limit as delta x approaches 0. Well, what is f of x plus delta x? That's just going to be c times g of x plus delta x, right? Minus f of x, which is just c times g of x, all divided by delta x. Well, this is, I'm just factor out a c, right? This will be the limit as delta x approaches 0 of c times g x plus delta x minus g of x divided by delta x. But what is the limit of c, right? We had a product theorem, we had a theorem for limits regarding products, right, in which we could simply pull this c outside the limit, such that this is then equal to c times the limit as delta x approaches 0 of g of x plus delta x minus g of x divided by delta x, which is just by definition c times g prime of x. That's a handy rule to have. It's an easy one to show. Let's try a problem now. Let's something that'll incorporate aspects of these first two, and I'll have this be a try at home. So let's let f of x be equal to 3 times x to the 4th. So go ahead and pause the video. Use these differentiation rules to solve f of x equals 3x to the 4th, and come back when you're done. So which of these rules are we going to use? Well, it's obvious we're going to use rule number 3 because we have a constant times a function, right? X to the 4th, that's our g of x, right? But we'll also use rule number 2. Okay, if we apply rule number 2, what is n? 4. So f prime of x is going to be equal to, using rule 3, it's going to be equal to 3 times the derivative of x to the 4th. That's using rule 3. And so that will be 3 times the derivative of x to the 4th. Well, we use rule 2 for that, where n is equal to 4. So we'll have 4 times x to the 4 minus 1. And that's just equal to 12 times x to the 4 minus 1 is 3, so x cubed. 12x cubed. All right, number 4. Do I need to do, I do need to do, yeah, let's just see. This is one that's good. So if f of x is equal to g of x plus or minus h of x, then f prime of x is equal to g prime of x plus or minus h prime of x. That one is pretty straightforward to prove. It's very intuitive and obvious. Maybe I'll leave that for a homework assignment, but we'll just move on. But let's put it to practice and see how it's used, because it's an important one. Because now I'm going to give you a problem to try at home. Let's let f of x be equal to x squared minus x plus 1. So pause the video, give that one a try, come back when you're done. All right, so this is one that directly uses property number 4. And normally we'll do this in much shorter order than what I'm doing. You normally don't write it out so verbosely, but we're going to write it like this for starts. F of x is going to be equal to, by differentiation rule number 4, the derivative of x squared, and then by a combination of rule 3 and rule 4, minus the derivative of x plus the derivative of 1. So I think we're using, I should have put a factor in there, then we'd have used all of them, right? Oh well, too late. So we just do it term by term now, right? And what do we get? Well, the derivative of x squared, right, using rule number 2 with n equals 2 is 2x to the 2 minus 1 is just 1, so we'll just write 2x. Minus the derivative of x, well, again, using the power rule, that's 1 times x to the 1 minus 1. X to the 0 is just 1, so we just write minus 1. And then plus the derivative of the number 1, that's a constant, so we use rule 1, right? And rule 1 says the derivative of a constant is 0, so plus 0, we just won't write anything. And so our final answer is 2x minus 1. Okay? I think that's all the basic differentiation rules that apply to polynomials and like for functions in general. I hope I'm not missing any. Well, let's hit some trig functions. Okay, I'm going to talk about the derivative of the sine and the derivative of the cosine. So that's something I think we should have early on. But it's going to require some material, some preface material. We're going to need to rely on the fact that the limit, as I'll call it h, goes to 0 of the sine of h over h is equal to 1, and that the limit as h approaches 0 of 1 minus the cosine of h, all divided by h, is equal to 0. Now, this limit follows from this limit. So if you can prove this limit, that the sine of h over h as h approaches 0 is 1, then you can prove this one. It's simply a combination of rationalizing the numerator and making the occasional trig substitution, and you should be able to demonstrate it. I'm going to leave that one for a homework assignment, okay, to demonstrate that this follows from this. But let's look at this. We talked about it kind of casually last time, but we can do a little bit better and be a little more rigorous about it, and that's what we're going to do now. So, but first let me just put up a nice circle, because we're going to use something called the squeeze theorem. Okay, and the idea behind the squeeze theorem is that if I can get some unknown function, right, at some point of interest, let's say that point right there, if I can find two functions that are always greater than and always less than that function, and I find what the limit of those two functions is at that point, I can squeeze, I can glean what the derivative of the unknown function's derivative is, in this case sine x over x, or sine h over h, by knowing the limits for the derivatives of these other two functions. And so that's what we're going to be doing here. But first, let me just draw a diagram here. I'm going to try to be careful. So this is going to be a point. So this point P is just going to be cosine. This will be theta. I don't want to over pollute it, but the angle that these two subtend is theta. And so, actually, let's make it h, because that's what we're using anyways, right? H times the sine of h. I want to drop down a perpendicular. And I'll make another point here. I'll call this point A. I'll call this point B, C. Okay, so, and this is the origin O. So notice that the area, I'm going to write A for area, of OBC. That's from here to here to here. That's a sector, right? And I'll talk about the areas of sectors in just a minute. Is less than or equal to the area of OBP. OBP. That, of course, is the area of a triangle, which is less than this larger sector, OAP. The area of OAP. So now it's just a matter of getting, we know what the area of this is. That's just the 1/2. What is the base of this triangle? Well, that's cosine h. Times the height of this triangle, well, that's sine h. So that is the area of OBP. Because I want to consider above and below this, I'm going to go ahead and take the absolute value of the sine, because it switches signs when we go below this axis here. So I'm considering basically positive and negative angles h, right? Yeah. But what about sectors? Well, the area of a sector, right, if you think about it, we know what the area of a circle is, right? Area of a circle is pi r squared. So if I have a circle, but what about a sector? Here's a sector, and we know, and so this will be some angle. So I'm going to call it theta this time, okay? So the ratio of theta to, what is theta for a whole circle? It's 2 pi, right? Theta over 2 pi should be equal to the ratio of the area of a sector over the area of a circle, which is pi r squared. So solve for area of a sector, right? And that tells us that the area of a sector is equal to, the pi's cancel, we'll get 1/2 r squared times theta. And so we'll use that to get these areas here. So OBC will be 1/2 times cosine squared, cosine of h squared, times the absolute value of h. Now the rightmost one, right, since this is a unit circle, right, the radius in that case will just be 1. And so we'll get 1/2 1 squared times h, absolute value of h. So we'll multiply everything by 2. That'll get rid of these halves. We're going to divide out by cosine of h times the absolute value of h. So everything is getting divided by cosine of h times the absolute value of h. Cosine of h, absolute value of h. Cosine of h, absolute value of h. And I just realized using cosine of h is a terrible idea because it makes them look like hyperbolic functions. The hyperbolic functions are sinh and cosh. But anyways, so that was a poor choice. So what do we get? Right, we'll divide out one of those cosines and we'll be left with the cosine of h over here on the left, less than or equal to, here we're going to have sine of h over the absolute value of h, less than or equal to, we'll have 1 over the cosine of h. And if we take the limits of the left and the right terms, what are the limits as h approaches 0? What's the limit as h approaches 0 of the cosine? The limit as h approaches 0, that's 1 less than or equal to sine h over the absolute value of h less than or equal to 1. 1 over the cosine, also 1. So we've squeezed the limit as h approaches 0 in between 1 and 1. What does that mean for this, the sine h over h? Well, by the squeeze theorem, it means that the limit as h approaches 0 of the sine of h over h is equal to 1. Okay. So we squeezed it in between two other things. In this case, we did it through these areas. So now we've got this, and like I said, you can do in your homework, demonstrate that this follows from this, and so we'll have this at our disposal as well, and we'll use it, we'll need it to demonstrate the following. 5. If f of x is equal to the sine of x, then f prime of x is equal to the cosine of x. But we have to prove that, because this is a math class after all, and occasionally we should have to do a proof or two. So let's set out and prove it. We'll use the limit theorem, the definition of a derivative in terms of its limit. So the limit as delta x approaches 0, well, what is f of x plus delta x? That's going to be sine of x plus delta x minus f of x was just minus sine of x divided by delta x. And so here we're going to have to use some trigonometric identities. You might recall that the sine of a plus b is equal to the sine of a times the cosine of b plus the cosine of b times the sine of a. Did I get that right? I think I did. So we'll write that out here. The limit as delta x approaches 0 of the sine of x times the cosine of delta x plus the sine of delta x times the cosine of x minus the sine of x, all divided by delta x. And so what I want to do now is I want to move this sine, minus sine x, over here. So I have limit delta x approaches 0, and I can factor out a sine, right? I'll factor out a sine of x, and that'll be times cosine of delta x. This will be minus 1, right? And then I'll still have down here plus sine x times cosine of delta x. Okay? So I just simply move this term here close by, factored out the sine x. So I got this, yes? Yeah. And now I'm going to split this up into two pieces. I'm going to have the limit. So this is equal to the limit as delta x approaches 0 of the sine of x times cosine of delta x minus 1 divided by delta x. Remember, we're going to use this definition here for that, plus the limit as delta x approaches 0 of, this time it'll be the cosine of x times the sine of delta x over delta x. So in looking at these limits, right, we know that this limit is going to go to 0. Okay? So that limit, that goes to 0, and we're left with this, cosine x times sine of delta x over delta x as delta x approaches 0. Well, that we have from here goes to 1, you see? And so in the end, all we're left with is just the cosine of x.
Okay.
So a little bit of work, but it wasn't too bad. I'll just write one more rule down, and that is that if f of x is equal to the cosine of x, then f prime of x is equal to minus the sine of x. And the proof of that I'm actually going to leave for the homework, because I don't think it's terribly hard to work out. Those are the rules, and I don't want to do the tangent yet, because we're going to, in the next couple of lectures, we're going to talk about the product rule and the quotient rule and the chain rule. And once we have all this stuff under our belt, then we can talk about the derivative of the tangent of x. Hopefully I did not leave anything out. I don't think so. So that's all I'm going to say about the basic differentiation rules. We will use them often. You will use them often, especially in your math and physics coursework. And next time we're going to talk about the product and quotient rule. So I'll see you then.